Alright, this is another one of the classic situations that we encounter in structural mechanics, and that is a simply supported beam, typically a floor beam of some sort. Particularly this one would go maybe from column to column with a midspan beam that frames in out of plane, which is where this concentrated force would actually be coming from, would be as a reaction coming from another beam that frames into this. And we're asked to derive the maximum deflection of a simply supported beam subjected to a midspan load. It's assumed that EI is constant, and we're going to find out that our max displacement at that midpoint is going to be PL cubed over 48 EI. But where the heck does that come from? Right? And so that's what we're going to start working our way through. It turns out that this is a fairly lengthy, well, it could be done in a short kind of way if we're really clever, but we're not going to do that. We're going to do it in a more formal kind of way. So we know, of course, here that our reactions are going to be half of the total load because of the symmetry of our scenario, and so that makes the shear diagram look like so. And we'll have P over 2 plus a positive up here, and down below, of course, it'll be negative P over 2. There's your moment diagram. And notice, to describe this as a function, you'd have to do something like this. You'd have to break it segmentally because we have two regions. The loading regime is not one continuous function unless you want to use discontinuity functions, which is a whole other thing to go learn, and they're okay. But in this region of X that's in the left half, then the shear is then P over 2, and the other one is minus P over 2. And you can actually get that just by observation. Right? When it comes to the moment diagram, of course, dm dx equals v, so the slope of the moment diagram equals the value of the shear. The shear is constant at P over 2, and so it's going, and the change in moment, P over 2 times L over 2 is that area there, so we'll have a max moment that is PL over 4, and then it decreases like so, back down to 0 like it should. And now this one by observation isn't quite as easy to maybe come up with. First part's not, it's y equals mx plus b, and of course it starts at 0, and so that's going to be P over 2x between 0 and L over 2. Alright, now the second one, well, it's a straight line, it's got to match, but if we just integrate that real quick, that's minus P over 2x plus some sort of constant. We have to get ourselves back to 0, and at L this would be minus PL over 4, so that probably has to be then PL over 2, so that has to be PL over 2 there. Put L over 2 here, minus PL over 4 plus PL over 2 would be positive PL over 4, so yep, straight line, oops. And there's your mathematical function for the moment diagram, right? It's kind of a pain, isn't it? I mean, breaking this apart like that, there's got to be a better way, and there is a better way, but we'll just keep on charging along here. That gets us the moment functions, right? So that's really step 1. There's step 2. Step 3 would be curvature. Right, so kappa equals m over EI. I'm not going to repeat all of those because that's kind of a pain just to rewrite all that. And then 4, let's find the slope. Right, now instead of the slope itself, because EI is constant, I'm going to make this a little bit easier. EI theta equals the integral of EI kappa. And so there's your, oh, we got to do this in 2 pieces. Oh, what a pain this is. Oh, and it is very much a pain. We've got P over 2 integral of P over 2x dx, and the integral of minus px over 2 plus pl over 2 quantity times dx. The first one now becomes px squared over 4 plus a constant, we'll call C1, and then this one is minus px squared over 4 plus pl over 2x plus another constant. Now here's where the continuity conditions are going to come into play, and that is, under this little moment diagram, we're going to get a nice little smiley face throughout, positive moment, so therefore positive curvature throughout, and we're going to then just get this little fella in there. There we go. And note that we have a nice smooth curvature that's going on right there, right? Just take a beam and we'll put a load in there, right, the midpoint, and bend it, and we get a nice little smiley face throughout. Nice, and we get continuous slope right there at that point. So that means at x equal to L over 2, my expression here to the left side, we'll call that theta 1, and my expression theta 2 for the right side, that theta 1 of x has to equal theta 2 at x. And you might say, well, and it's also equal to 0. Well, it'll turn out to be, but I'm not going to presume that. I'm going to prove that that would turn out to be the case. And when we do this, what's going to happen is we get p over 4 times x squared, which is now L squared over 4, plus C1 is going to be equal to minus p over 4 L squared over 4 plus PL over 2 times L over 2 plus C2. Right? This is all a big gigantic pain. There's no doubt. We get a p over 4, L squared over 4. There's a negative that comes to the other side, so we have 2 of those. Alright, so that's PL squared times 2 over 16. Right? 1 over 16, and that comes over there. There's 2 of those. And then we get this one. That's PL squared, and that's L over 4 plus C2. Right, so what we're getting out of this is an expression between C1 and C2. This is 1/8, and we take it to the other side, and what we're going to get is that C1 equals PL squared over 8 plus C2. I sure hope I got that right, but I think I did. That's 1/8. Take it. That's a positive. Take it to the other side. 1/4 minus 1/8 is a 1/8. That's all over here. So now we have a relationship between those two constants using this continuity condition. I don't know anything else about them, but I know something about those two constants right there. And I don't have any other boundary conditions here. The boundary conditions are that v at x equal to 0 equals 0, and v at x equal to L equals 0. Those are my only two displacement boundary conditions. So let's now go figure that out then. Alright, well, we've got for step 5, we'll find the displacement, v, and v, of course, is equal to the integral of theta dx, and that, unfortunately, is segmental, so we got to take our expressions that we found. I'm going to leave them like I had found them already. Right? I'm not going to mess around with all the C1, C2 business just quite yet. And so we got the integral of p x squared over 4 plus c1 dx, and this one is the integral of minus px squared over 4 plus pl over 2x plus c2 all times dx. Oh my gosh, what a pain this is. I keep saying that because it is. Alright, we got px cubed over 12 plus c1x plus c3. That's the first one. Second one is minus px cubed over 12 plus plx squared over 4 plus c2x plus c4. Oh my gosh. Wow. Zowie. Alright. Well, now what the heck do we do with this? Well, now we can start going evaluating a few things. For instance, boundary condition at 0. V is 0 equals p times 0 cubed over 12 plus c1 times 0 plus c3. That's the only one left over. It's supposed to be equal to 0, so therefore c3 equals 0. Woo! Like that. And get rid of one. So that's kind of nice. And now we can actually substitute in that we know C1 from over here. Right, so we'll get px cubed over 12 plus C1 times x. So that's PL squared over 8 plus C2 all times x. I don't know if that's helpful or not, but we're going to use it temporarily anyways. Alright, so now what? Well, now we can go look at V at L over 2, which is going to be equal to P over 12 times L over 2 cubed plus, and then we get PL squared over 8 plus C2 times L over 2. Alright, that's V1. That's when we look at the left-hand side of things. When we look at the right-hand side of things, so what does that tell me anyways? PL cubed. You know, you're probably asking me, what'd you do with the EI? Well, you're right. I'm a little sloppy here. That's what I did with the EI. Alright, so now look at the, let's get this a little bit closer to being evaluated. That's 2 cubed, that's 8. 8 times 12 is 96. Plus then, yikes, PL cubed over 16 plus C2L over 2. Looks to me. And I don't know, does 16 go into 96 real quickly? Oh, it does perfectly. So that's going to be equal to 7PL cubed over 96 plus C2L over 2. Oh my gosh, this is painful, isn't it? It's very much painful. Let's look at what happens with the second one, which is going to be even worse. Right, we got all this nastiness. So minus P over 12 times L over 2 cubed plus PL over 4 times L over 2 squared plus C2 times L over 2 plus C4. Now these two have to be equal to each other. Oh my gosh. Alright, well, alright. This is minus PL cubed over 96 plus PL cubed over 16 plus C2L over 2 plus C4. And that, then this is 6 over 96. So that now is 5 over 96 PL cubed plus the C2L over 2 plus C4. And these two have to be equal to each other. Well, that actually is kind of convenient because look, these two have to be equal to each other because that's the continuity condition at the middle. That means the C2L over 2's both cancel out, and we're going to find out if that's the case that C4 then would have to equal the difference between these two. This is on the left side, this is on the right side. Take it over, we'll get 2 over 96 or PL cubed over 48. How about that? That's kind of bizarre. I wouldn't have predicted that. But okay, we've got that. That's very interesting. Now, we can come along, and because we still don't know what C2 is, and so EI via 2 at L then has to be, that's the second boundary condition, that's minus and PL cubed over 12 plus PL cubed over 4 plus C2L plus C4 has to be equal to 0. Right? This is, we know this is a PL cubed over 48. And so this would be minus 4 over 48. This would be 12 over 48 plus 1 over 48. PL cubed plus C2L equals 0. And so that's going to be an 8, that's going to be a 9 over 48. And so it looks to me like C2L equals minus 9 PL cubed over 48. Or that C2 equals minus 9pl squared over 48. Interesting. So now let's see if this really works out. I said that delta max was PL cubed over 48 EI, that it happens at the middle. Of course, we're going to go back and we're going to substitute in to our slope expression and see if we really get zero slope at L over 2. So let's see if we do, now that we know what C2 is supposedly equal to. So let's check it out here. Theta 1 at L over 2 is going to be, there's my expression, there it is. Right? That was P over 4 times L squared over 4 plus C1. We found out that C1, did we ever actually find it? Well, I guess we didn't. We had a, this is EI times that, by the way. We've got a PL squared over 8 plus the C2, which we said was minus 9PL squared over 48. Right? Well, this is 1 over 16 plus, this is 1 over 8, and of course we have the minus 9PL squared over 48, and so now that's going to be equal to PL squared, and 1 over 16 is 4 over 48 plus 6 over 48 minus 9 over 48. Yeah, uh-oh. Well, that's because it's not 4 over 48. 16 is a 3 over 48. Oh, good. That equals 0. Right? So that was, we've demonstrated that the slope is 0. We didn't actually prove it, but we demonstrated that it was 0 at L over 2. So that's good. And now let's go find out if we get PL cubed over 48 for the max at the middle. EI V1 at L over 2 would be equal to P over 12 times L over 2 cubed. Now, didn't we already evaluate this? I think we did. Forget this nonsense of starting all over. I've got it right here. It's equal to 7PL cubed over 96 plus C2L over 2. And we found C2 is this. Right? So, using this one right there. So this is minus 9PL squared over 48 times L over 2. And that'll be a 96, so we're going to get here a 7 minus 9, so that'll be a minus 2PL cubed over 96, and that is minus PL cubed over 48. And of course, there's your EI over here, that our delta max then is equal to PL cubed over 48 EI going downwards. The negative told us that it was going downwards. Right? Wow. Right, this is actually not that hard of a problem to do, but if you want to prove it using the integral calculus approach, it's a pain. Now notice something here. If turns out that theta at the middle equals 0, right? And if that's the case, there's another situation out there that looks very much like the same thing, and that is a cantilever beam, right? That has theta of 0, doesn't it? And our concentrated load then would be out here, P over 2, and the deflected shape then, yeah, you like that? Ding, is the same thing we just found, where this would be our delta equal PL cubed over 48 EI. Now you got to be careful here. The L of the entire beam, and if you go look up this equation here, it'll be PL cubed over 3 EI, but the L will be different. This is an L of L over 2 for that segment. That's how you'll see in the textbooks people derive this thing, and they'll usually in the tables only give you the equation associated with the left half for a variety of reasons. One of which is they're lazy. They don't want to do all this segmental stuff, and so they'll derive it using something like this, and then they'll transform it over to this space. But also because if you know what the displacement function is here, then you can always find it over here by a mirror image. That's not the lazy part. The lazy part is just not showing all the work because it is long and tedious and difficult.